speaker. Our second speaker is Jörg Endrullis from the Vrije University in Amsterdam, who's going to be talking about the complexity of equivalence of specifications of Internet objects. Yes.
Okay. Thanks a lot for the introduction. And this is joint work with Dimitri Hendricks and Rena Bakshi from the Vrije University. So, as a prime example of infinite objects, we will focus on streams, infinite sequence of elements like we've seen already, and we like to specify streams by means of equational systems. So here we have stream constant m, x, and y, and we have a stream function merge that alternatingly interleaves the elements of the streams. And in this case, we can actually turn this equation specification into a rewrite system by applying the equations from left to right, and then the stream constant m rewrites in the limit to the well-known two-more sequence. And the question we are addressing is, given two systems of equations, how difficult is it to decide whether they define the same stream? Of course, these are undecidable problems, so we pinpoint their complexity in the arithmetical or the analytical hierarchy, respectively. The idea of these hierarchies is to classify problems by formulas. So in the arithmetical hierarchy, we have number quantifiers in front of the decider predicate. In the analytical hierarchy, we have set quantifiers in front of an arithmetical formula. So let's look at two examples. The class pi02 of the arithmetical hierarchy. The pi tells us that we start with 4 quantifiers. The 0 says we're in the arithmetical hierarchy, and the 2 tells us that we have 2 quantifiers. So for all x exists a y such that some decidable predicate exists. And this is a well-known class. It's the class of the totality problem for Turing machines. For all inputs, there exists a number of steps such that the Turing machine terminates. Let's also look at the class of the analytical hierarchy, the class pi11. The superscript 1 tells us we are in an analytical hierarchy, and the subscript now counts the set quantifiers, so we have 1 for all set quantifiers. And the class pi11 is the well-known class of the well-foundedness problem. So given a decidable relation in the form of a Turing machine, the task is to decide whether this relation is well-founded. Okay. First, let's look at related work. In 2006, Grigori Rojo had an ICFP paper with the main result that proving equality of streams defined equationally is pi02 complete. And we got interested in this paper because we recognized that the problem is actually easier if the streams are defined in a productive way. Productive means that the streams can be obtained by evaluation or rewriting. So you could imagine that the streams are given by a program that produces an infinite sequence of output. And if you have such programs, then in order to compare whether they produce the same output, a single for all quantifier is sufficient. And if you look in the pi02 hardness proof that Rojo uses, then you see that he employs specifications that have multiple solutions. And that raises two questions. What is a solution, and what is the notion of equality? So the notion of equality that he uses is a semantical one, namely behavioral equivalence in all stream models. What's a stream model? First, Rojo defines stream algebras, and he looks at bit stream specifications. So stream algebras consist of a domain, and for every symbol of this specification, and interpretations. The domain consists of 0 and 1, the interpretation of the bits, and the set S that contains representatives of streams. And I say representatives because they have some head-tail behavior. So the interpretations include interpretations for head and tail. So head is a function from S to 0, 1, and tail is from S to S. And two elements A, B in such an algebra are called behaviorally equivalent if for all n, the head of the nth tail of A is equal to the head of the nth tail of B. So with head and tail, you cannot distinguish this element. And such a stream algebra is a model of a specification if for all equations in the specification it holds that the interpretation of the left-hand side is behaviorally equivalent to the interpretation of the right-hand side. So it does not need to be equal, but the two interpretations need to behave the same with respect to head and tail. There's two things important to know about this semantics, namely the behavioral equivalence is not a congruence, and equational reasoning is not science. So for example, there are models of the specification A is equal to 0 of A that do not fulfill f of A is equal to f of 0 A. And this might look surprising, but actually it's not a bug, it's a feature. Roche employs this in order to model non-determinism. So Roche uses underspecified function like the f here to model non-deterministic functions. And indeed, if you think of f as non-deterministic, then one would not expect this equality. This implication error here can be given a formal meaning, namely that specification implies an equation S is equal to T if the equation S is equal to T holds in all models of E. Okay. This is actually one of the stream models which show that this implication does not hold. But let's not go into detail here. The idea is just that you have two elements in the domain that represent the string of zeros. Here it's Z and 0 to the omega. Both have the same behavior with respect to head and tail. But they are different, and then F can map them to completely different strings. We recognized, however, looking at Roche's paper, that the semantics that Roche uses does not go well together with function definitions using pattern matching. This is actually an example from the paper of Roche. You have the string of zeros, the string of ones, and string link of alternating 0, 1, 0, 1, and so on. And then if we alternatingly interleave the elements of zeros and ones, one would expect to obtain the string link. However, we found a counterexample to this implication, and the problem is that merge is defined only on streams that can be constructed using the string constructor. And as you see in this model above, we can make behavioral models where there are streams that cannot be constructed by the interpretation of the string constructor. So here we have Z is a stream behaving like a stream of zeros, but Z is never the result of applying the interpretation of the string constructor. Does this mean that the results of Roche were flawed? No, it does not mean that. There's a very simple fix for this, and the fix is to avoid pattern matching and to instead define merge using head and tail equations. And if you look at the other papers that of Roche, then you will see that Roche actually never uses pattern matching, only in this ICFP paper. And yes. So this can be fixed. Nevertheless, this was motivation for us to look for alternative definitions of string equality. And what we were looking for was something that should be simple, it should allow for equational reasoning, and it should allow for pattern matching in function images. We use the same basic setup, so we have systems of equations with sorted terms, with sort S for streams and D for vectors, but we use a different notion of stream algebras. We also have a data domain, which for bit streams would be 0 and 1, in general it can be some initial algebra. But we use a different string domain, whereas Roche had this set S of representatives of streams, we use a stream domain, real streams. So the stream domain consists of streams over the data algebra. And we call this stream algebra full if it contains all the streams over the data algebra. And then it's very simple to interpret symbols of our specification, namely just by functions over data and stream, according to the sorts of the symbol. And the only interpretation we fix is the interpretation of the stream constructor, namely it should construct streams. And then we have the standard notion of model, such as stream algebra as a model for specification. If for all the equations in the specification and every interpretation of the variables, the interpretation of the left-hand side is equal to the interpretation of the right-hand side. Using this semantics, we suggest different notions of equality, namely two semantical and two rewrite notions. The semantical notions are equality in all models. We will see on the next slide what this is. And we can also look at equality of the set of solutions, and they are slightly different. And if one does not want to use semantics, then there are also interesting notions for equality based on rewriting, equality providing productivity, which we've already seen. And there is observational equality for lambda terms, and there we actually base ourselves on previous work. and we just analyze how difficult it is to decide these notions. For the semantical notions, we can moreover distinguish whether we look at all stream models or we look only at full models that contain where the stream domain contains of all the streams of the data sets. Okay, equality of all models. So we have a specification and we want to know whether some equation M is equal to N holds. Equality in all models means that this equation should hold in every model of E. When is this interesting? It's interesting if we have, for example, two streams that are defined interdependent, so they depend on a common unknown. So for example, here we have M depending on the unknown X, and we have N also depending on the same unknown X. So if we want to know whether M could be exchanged for N, whether they have the same behavior, then we have to interpret them in the same model simultaneously, that the model chooses X the same for both. However, it has also strange effects. Namely, if you take just a renamed copy of a specification, then this is not considered equal with respect to this semantic. For example, here we have M is 0 tail M and N is 0 tail N. Both of them have infinitely many solutions, and in one model you can choose a different solution for M than for N. And it depends on your application whether you want to consider them different or you want to consider them equal. If you want to consider them equal, then a better semantical notion is equality of the set of solutions. So then the set of solutions for M is the set of interpretations of M in all models of the specification of M, and the same for N. This is especially interesting if M and N are defined by two different specifications. I mean, if you put two different specifications together, then you might mess up the semantics because you increase additional constraints on the domain. And it's a very well-known notion because it's actually the standard notion if you think of equations of real or complex numbers. Then we consider two such equations equivalent if they have the same set of solutions. The rewriting notions, we've already seen rewriting providing productivity, the equality providing productivity. So if we know that we can evaluate both streams, both specifications, and then we just have to compare the output that they produce. And this is the natural notion if the specifications are given in the form of a rewrite system. And it's also conceptually nice because it separates the problem of well-definedness, namely productivity, from the problem of equality. And the second rewrite notion of equality that we have looked at is observational equality for lambda terms. So we have different versions of this. Let's look at the first one, the equality H. So two lambda terms M and N are equal with respect to this H equality if for all context C of M has a head normal form if and only if C of N has a head normal form. So we put the lambda terms into context and then we observe their behavior. And the observation here are head normal forms. And you can do the same with normal forms or weak head normal forms, and there are other variations possible. These notions have not been invented by us, but they go actually back to a paper of Desani and Giovannetti in 2001, where they also showed that these notions have a strong relationship to different notions of Böhm trees. So Berarducci trees, Levi-Longo trees, Böhm trees, eta Böhm trees, and eta infinity Böhm trees. And you see here that for some of them there's direct correspondence, and for this weak head normal form notion there is no direct correspondence known yet, maybe there exists one, but still it has a close relationship to the Böhm trees. Let's look at one example. So you can think of this x, y, and g as lambda terms, but we wrote them here as rewrite rules for better readability. The point is that g is something which does not evaluate to anything, so it's undefined. And x and y rewrite to the stream of natural numbers, where every second element is undefined. And the difference is just that the undefined elements in X are G of 0 and the undefined elements in Y are G of n. Nevertheless, it does not matter how the undefined terms look like, both have the same Böhm tree, or the same Bernoulli tree, and therefore they are, according to this picture, this has the same Bernoulli tree, equivalent in all these three notions. And why are these notions interesting? The point is that they're especially interesting for function programming because, as Desani and Giovannetti argue, that especially this notion with respect to weak hat normal forms corresponds closely to having equal behavior in lazy functional programs. So if you want to know whether you can exchange one term for another in a functional program, then then you should use this notion equality with respect to the weak hat normal forms. And what is the relation to the semantical notions? These two terms, x0 and y0, are not equal in any of the semantical notions that we see, not the ones that we suggest and also not the one suggested by Rochu. Because the reason is that here, in x, every second element is undefined as g of 0, so they are all the same, so they have the same interpretation, these bottoms. But in y, the undefineds are all different, so you can give them different interpretations in the semantics. So somehow the semantics also tries to give interpretations to undefined elements, whereas in functional programming, if you look at interchangeability, if a part of a lambda term does not evaluate to anything, you don't care what for undefined term it is, it just doesn't evaluate. Okay, the results, so we investigated the complexities of these different notions, and the surprising result was that they have an extreme range of complexity. So for the rewriting notion, we have complexities in the low levels of the arithmetical hierarchy, equality providing productivities pi01 complete, so one for all quantifier. This observational complexities and the Böhm tree complexities that we, Böhm tree equality that we've looked at are pi02 complete. There's actually one thing open. We did not look at the Bernoulli trees, and we conjecture that they are probably at one level higher of the arithmetical hierarchy. But for the semantical notions, we found that the complexity jumps to the analytical hierarchy. So equality in all models is pi11 complete, so this is the class of the well-foundedness. And if we consider full models, then we even go completely out of the roof. So then this complexity subsumes the entire arithmetical and analytical hierarchy. And why is this more complex? You could say that if we force the models to contain all streams, because the equations in the specification, if they contain variables, then these equations have to hold for all assignments of the variables. So if we know that the models are full, then this is a strong condition on these equations, that they have to hold for all stream assignments. Is there enough time? Or I should probably wrap up. So the idea for the proof of the pi11 is to reduce the well-foundedness problem, and the crucial point is that the quantification over all models, because the model determines the interpretation of the under-specified functions. Then you can use some stream constant x that is under-specified to guess a non-well-founded path through computable relation. And the idea for the subsumption of the whole analytical hierarchy is a bit more complicated. So the first thing is we eliminate existential quantifiers by skolemization. So we introduce just one existential function quantifier in front. This existential function quantifier then translates to the question whether there exists a model, because the model chooses the stream functions. And these for all quantifiers, they translate to equations with variables. Okay. The conclusion is there are many interesting concepts of equality that have largely different complexities. There is no best notion of equality. It always depends, I hope I conveyed this a bit, that it always depends on the application. So if you want to model non-determinism, then none of the suggestions that I've shown will help. So then you have to go for the models that Rochu suggested. And if you are interested in exchangeability in functional programs, then probably you will not go for the semantical models, but for these equalities that Desani and Giovanetti have suggested. Thanks a lot for your attention.
Thank you.